Show you is what solar installers would do to generate a national electric code report. Design software is free to use if you want to save your content. It is that's when you have to sign up for it. National Electric Code Report for this exercise. So here's Half Moon's rooftop. And let's just assume for the simplicity purpose that they're a perfect rectangle that is about 106 feet long by about 23 feet deep, just for brevity. So 106 by 24. And we're not going to go and add any obstructions or anything like that. It was a microinverter array using a 250 watt panel. So let's just go ahead and pick out, here's a 245 watt panel. No worries on that. And here's a in-phase microinverter. So this might not have been the exact system we did a few years back. And then let's go and put in our fire code clearances of 3 feet off the rake and 3 feet off the ridge. And since we're talking about code class, there are other parts of code beyond National Electric Code. Like for those who are here for the NABCEP continuing education, you're well familiar with the 3 foot offset rules, 3 feet off the sides of the roof, 3 feet off the top of the roof. And that's when there is no forced air ventilation system to ventilate smoke during a fire out of the attic. If you don't have a forced air ventilation system, you have to have clearances on your rooftop for fireman access. And that's not part of National Electric Code. It's still part of code. There's National Fire Code, of which Electric Code is just a subset of it. Let's just quickly build out some microinverter circuits. We'll just make this small. Don't know how to make that any. There we go. All right, so we'll do 17 and then 17. Why don't we just go ahead and make that, try 14 and 14. So we'll do a 15 circuit and a 14 circuit, another 15 circuit, another 14 circuit, another 15 circuit, another 14 circuit. And so that's our solar array. And we could go and fine tune it further. So I just want to get to the National Electric Code document. So here we are with our balance of system components. And we'll say, okay, well, we're transitioning at the array into the attic. And the question is, well, why is that important? What's the difference between being up on the rooftop and being inside the attic? Well, we've seen that there's the roof is a wet condition and the attic is a dry condition. And furthermore, there's another part of code that says, hey, if there's moisture in the air outside your house and then you have a drier air-conditioned space inside the house, that difference in moisture alone is going to cause the higher pressure moist air to be kind of going into that conduit and then condensing. And where's the water going to go? It's going to drop down the conduit. And so you have to seal conduit going into the roof, into the attic with a little sealant that you spray. Also, underground conduit coming up from the ground into a dry space or into the attic. I've seen a cabin with underground feeders coming up where it's just between the underground feeders and the cold shaded concrete to the atmosphere in the south where it's hot and humid outside. You open up the line side tap box and there's a puddle of water inside what you think should be a NEMA 3R weather rated box. And that's just because the humidity alone can cause it to rain inside your equipment. And so even though it's a weatherproof box, you still may need to install a weep hole inside the box to get the moisture out of there. So anyway, to answer all questions of electric code, we're saying, okay, well, we're going into the attic at this point. Let's say we're doing a supply side connection. Do we want to use a fused disconnect or a breaker box? Well, now we know that either one is a main overcurrent protection device. And so why don't we just go ahead and use a breaker box since we have multiple microinverter circuits. And, our grounding system, let's say we're using a grounding system with racking where the grounding is built into the racking itself. Then we get into wire and conduit options. And this stuff is Greek to me. When we get into National Electric Code conductor selection, there's going to be all these acronyms, and you don't know what the acronyms stand for without industry experience. But what they stand for are the temperature ratings and the environmental condition ratings, and whether it's a wet or dry environment, and the voltage ratings for that matter. Is it a 240 volt or 300 volt cable? Is it a 600 volt cable? Is it a 2000 volt cable? And so we see in this particular solar design software, we see a survey where it's already, it's saying out of these three cables, which do you want to use? And what this is telling me is if I have no clue what cable to select for my system, it's telling me that these are common cable types to select. And what we'll learn later is the W in these cable types refers to a wet condition. And that little -2 refers to a sunlight resistant rating. And it turns out that all of these cables are rated for an appropriate voltage to be outdoors in a wet environment in exposure to sunlight. What I'm trying to say is if you're, as a learning tool, solar design software can kind of coach you in the right direction towards code compliant design. I used to be afraid of this stuff that it would make a mistake and not have something in it that was important to code. We'll be covering those sections, coming through those sections, but it does make a useful guide. So anyway, then we get to our branch circuits and we see there's questions about, well, how close is the conductor to the rooftop? Well, there's different temperature derating requirements that have actually changed in NEC 2017. There's a substantial temperature derate for being from 0 to 0.5 inches above the roof, and this middle range from 0.5 to 3.5 has kind of gone by the wayside. But in 2014, there's different temperature ratings for these different levels. So anyway, we're going through the building interior, then to the utility disconnect and breaker box output. We'll just go through the building interior. Then we get into our voltage drops, and these are our links of the building. So going back to Google Earth, let's just assume our branch circuits are running 55 feet, and then to the point of interconnection, that's 27 feet, and then maybe 15 feet down from there, plus slack. The worst case scenario, we're looking at 50, 80, 90, about 100 feet here for our branch circuits. And this is going to have a really good reward at the end. Transition box to the sub panel. Our 6 branch circuits, microinverter branch circuits, are going down to the building the combined output of the inverters to the sub panel, that point of interconnection is going to be pretty close. So we provided some more site information that has to do with code. And now it's calculating our conductor sizing. And, you can't rely on software alone, but then again, it does make a heck of a guess, like as a guidance. Like that in-phase microinverter cable is number 12 AWG, and it has a little bounce of system box that only takes number 12 AWG. And so what I'm seeing is it's all right. It's within range to do number 12. And then I'm in number 2 when these things combine. I'm looking at my conduit. It's all 1/2 inch, then 1.25 inch. All this stuff is fine. And where the payoff is with this particular software, which again, you could be doing this now along in class if you want to. It's just, it's free to use. It's just if you want an account and you save your work, you got to pay for it. It makes a great tutoring tool. Now what we have is a let's see. What we need is to export the code report and the payoff that I really wanted to illustrate here. In other classes, we go into the one-line diagram that may be contained in this or not. But in this course, what I want to highlight is, right now we're doing a start-to-finish read-through of all the nits and bits of National Electric Code. But if you want to cut to the chase and start with the calculations that are most relevant to solar design, your solar design software can guide you on that. So here we have National Electric Code references where you can't exceed 600 volts. And it goes into the voltage calculation for Article 690.7. And that's the solar specific section of 690. And hey, look, here's the ASHRAE database temperature. So that's pretty useful. Well, then on top of that, we get into the current calculations. Like, what is the continuous current of a solar array? Well, it says we have 14 microinverters at 0.9 amps each. And so it's 12.6 for the output current circuit of those inverters. Then we look at the based on what wire selection we've used, it runs the calculations for you and gives you what those calculations are. And so, this is calculating the, taking into account the 75C terminal that we talked about earlier. As we get into the next sections for the rest of the day, we're going to be getting into overcurrent protection device and equipment ground conductor sizing. And this report has all of those calculations as well as code references. Here's 240.4D, which we haven't gotten to yet. And then we have those calculations for every branch circuit on the rooftop. And now what we need to do is get down to the, not from the circuit to the combiner, but now we're at the main service panel to the point of connection where we've transitioned into the number 2 copper. And what we see is that our equipment ground conductor is undersized. And we see our conduit sizing And what we'll see in the next couple of sections of code under the general sections, that's all in sections 2 and 300 and 400. So we have, it's getting into the 90C conductor D-rate factor, the fill factor, the output ampacity adjusted for temperature and conductor fill. Getting into the table 250, which we haven't gotten to yet, which is the equipment ground conductor sizing of number 8. And then also getting into things like conduit fill calculations as well. And I guess this is, I'm not sure if it's referencing the table or not, but we'll see it in a bit.